Okay, welcome to everybody. My name is Franco Bagnoli, and I work in the Department of Physics and Astronomy, University of Florence, in Italy. My mail address is franco.bagnoli@unifi.it, and you can clearly contact me when you want. And this course will be about statistical physics in all several, say, point of views. And from a computational perspective, I mean that we shall use and develop computer programs in order to illustrate the different types of properties of statistical systems, or in general, system composed by, in general, many degrees of freedom, many particles. You can find all the material that you may need in this website, teaching.complexworld.net, and your home courses, introduction, stat phys, but you can find this just in the front page. And so there are a lot of lessons for the moment that I planned. I don't know if all of them will be of the same size. Probably some of them will be longer, other shorter. And so in a sense, they are about 15 2 hours lessons. And I shall also give into these into the pages that are not still present of this course all the material that I'll show in this course. And so let's start with a general introduction to this course, so that I can illustrate the path that we shall follow, so you can say realize where we are into the path that we are following. So let's start about physics. You study physics, and you know that physics is about reality, what happens around us. But actually, we are not really studying the reality. Clearly, when we perform experiments, when we perform observation, we are dealing with reality. But when we think about them, perform computation, or even just try to understand what is going, how to forecast what is going to happen, for instance, we actually use models. Models are, say, relationships among different elements, in particular when we use mathematics about relationships among variables, which represent only certain aspects of reality. Clearly, we have to restrict these for two reasons. First of all, because our mind is not able to understand a system composed by a large amount of elements. And second, also, neither our computers are able to simulate these. For instance, clearly, we could start from the very beginning, say path integral or quantum mechanics, and from that obtain all the reality, but this is impossible. So actually we use very simplified models because as some, I think Feynman already said, things has to be as simple as possible, but not simpler. So clearly we know that our mind is limited, and a lot of different experiments and measurements reveal that actually we can manipulate a very few amount of symbols. For instance, the magic number is about 7. So if we try to manipulate more than 7 items at once, or to play a game that imply more than 7 things to control, we are lost. For instance, for this reason, we are not really able to understand how computers play chess or play Go or play complex games, because clearly they do not have these limitations. And so we have a lot of problems in understanding, for instance, computers, even though we built the computers. So when we design a model, we try to keep it as simplest as possible. And also another characteristic that we exploit a lot is linearity. Linearity means that if someone has grown at a certain rate in the past, we expect it to continue to grow. If decreases, if it decreases, we expect it still continue to decrease, and so on. And actually, if you think, most, if not all, so essentially models that you have met studying physics are linear systems, or if they are not linear, they are manipulated in order to reduce them to linearity. Clearly, nowadays we have computers, and so we can implement models in computers, and we may ask if this will help us to understand better what is going on or not. Actually not. We can simulate, we can build very complex programs that probably represent well what happens in the reality, but this will not help us to understand things, because in this case we still again have a complex system and our mind has difficulty. This does not mean that we cannot simulate, but if we want to understand, we have to keep things simple. Okay. Clearly, we, from the time of Newton, we understood that reality is quite so can be manipulated using mathematical tools. Actually, someone still considers if mathematics is essentially an experimental science, and so our brain have been selected in order to understand mathematics, or if it is really universal and so not related to experiments, to experiences. Okay, but in general, we have our tools that, as Newton discovered, do not solve completely the problem. Clearly, we can have all the tools that we need to write down the equation of motion or the evolution equation of our system. This does not imply that we are able to solve them, say, by hand. And so we, luckily, we have now computers. We can integrate equation numerically. Actually, this has been done also by hand, for instance, by astronomers who were able to integrate the equation of motion of planets and forecast, I don't know, eclipses, conjunctions, and so on. Okay, but we have computers, and we want to start investigating complex systems, essentially statistical physics, by computers. And clearly, we have to represent our problem into a sequence of instructions. So clearly, we have to think how to represent what we usually manipulate by hand in computer language. And clearly, this is not an easy task, because computers have different ways, for instance, of representing numbers. They do not work really as with real numbers, but only with floating point numbers. They do not know how to say, okay, now with computer assisted algebra system, we can also teach computers how to derive, to make derivatives, but in general, we have to anticipate this computation and prepare the computer in order to have all easy for us computation done. And clearly we have seen a lot of improvements in our capability of, for instance, forecasting weather by using computers, and also by using a very accurate and measurements of the actual situation with a fine grid, because we need a lot of data. And also clearly in biological sciences, chemistry, physics, we had quite a large success using the computers. So we want to apply this in order to investigate statistical physics. The adventure of computers and physics is relatively old. They started about in the 40s in Los Alamos, where the equipe guided by von Neumann, the man here, developed the first computers. There were kind of computational tools also before, essentially analogic integrators, in which one builds up a specialized circuit, a specialized computer for each problem, essentially for integrating differential equations. But von Neumann developed the architecture of computers that we know now. I mean, a CPU, a memory, and a set of instructions of programmable computers. They also contributed to build some of them. IBM also clearly helped. And so, near the end of the Second World War, they had at their disposal computers that helped them to, for instance, compute the effect of an atomic explosion. And for this, they developed also special techniques, Monte Carlo techniques, that we shall study in one of the future lessons. And essentially the names of Ulam and Metropolis are related to this technique. Actually, I think that Monte Carlo was chosen as the name for this method because the uncle of Ulam used to play at the Monte Carlo casino and to lose money. And so they were joking about using dice, random numbers, in order to perform computation. And since von Neumann was always joking, I think that he chose this Monte Carlo name. Okay, and in the same, just after the end of the war, there was the first theoretical investigation using computers done by Fermi, Pasta, and Ulam. Pasta and Ulam are both, I think, mathematicians. And there was also a woman, Tsingu, who was a programmer, because most of programming were implemented by women that worked as first as a typographic device, then as human calculators, and finally as programmers. And the idea of Fermi was to check one of the main concepts of statistical mechanics, as we shall see in one of the future lessons, that is the equipartition of energy. And one of the main assumptions of statistical mechanics is that if you wait long enough, energy will distribute on all degrees of freedom. Clearly, if the system is non-linear, because linear systems do not have equipartition. But what Fermi was considering, how long does it take to have this equipartition? Because clearly, if it takes a few nanoseconds, you can assume that you are essentially in equilibrium just after a few time steps. But if it takes, say, the age of the universe, clearly you are not in equilibrium, you cannot use some of the tools of statistical mechanics. And so, since you need the nonlinear system, you had to use computers because by hand were not able to integrate the equation of motion for long enough. So they had to develop this program for simulating a chain of oscillators. And what they saw was that at first the energy seemed to distribute among the normal modes of this chain, I mean the oscillations. But after a certain time, they tend to return to the initial state, almost to the initial state, and then relax and then return. So there were a lot of oscillation. This depends clearly also on the energy of the system. If the energy is high enough, it goes much more easier to equipartition. And actually, we shall see that this was one of the objections moved to also to Boltzmann. And so, essentially, this is a really interesting point. Another notable date is 1963, when Lorentz, who was a meteorologist and was developing a simple system for representing the convection cells in the atmosphere, and noted that this behavior was not what was expected, basing on what was known at that time. I mean, what was able to be discovered by hand, because at that time, as we shall see I think in the fifth or sixth lessons, is that for with linear systems or also non-linear, but low dimension that can be investigated by hand, you may expect to see fixed point, oscillations, cycles, but actually not something that Lorentz observed in this first simulation. I mean chaos. Chaos means that you cannot forecast what is going to happen for a long time, and so essentially he started discovering a completely new field, again due to computers. And so essentially these are, now we are about lesson 6 or something like this. So we are now ready to investigate the goals of statistical physics, which, I mean, the idea of studying system composed by many parts. Actually, strictly statistical physics deals with in system composed by an infinite number of parts that can be studied clearly using both analytical and computational methods, and can also give suggest new methods for studying other problems, like in the case of simulated annealing. Clearly, we shall investigate this system from a quantum mechanics point of view, essentially by exploiting the fact that quantum particles are indistinguishable and also can be excluded or not according if they are fermions or bosons. But we also shall investigate system composed by classical particles, which are appropriate when, say, atoms or molecules are large enough and for temperature that are large enough with respect to the absolute zero. And we shall also develop concepts like phase space and clearly the role of time. Okay, but we shall, I said that we shall make use of computers, and in particular, we shall use a very simple simulating system, open access, that is called NetLogo, that we shall study in the second lesson, the main characteristics. And with this system, we could easily simulate the system in 2 or 3 dimensions, although the velocity is not really very high. And so we shall start with the classical framework, Newton law, force equal to mass times the acceleration, and we shall apply this first for developing the computational technique to very simple models, and then to models composed by a large number of particles, so that we can recover, at least qualitatively, the behavior of a macroscopic system. And so essentially we shall see that according to the temperature, we shall reproduce the main characteristic of a law, of a gas, of a liquid, or of a solid system. So we have seen that the same system, for instance, the Lennard-Jones system, that the gas or the liquid or the solid that we have seen before, is the same system, but according to different regimes, according to, for instance, different energy, they can behave quite in a different way, and we prefer to model them using a few degrees of freedom system. Another example is, for instance, that of a planet. A planet is often successfully modeled considering it as a point-like body, but actually it is composed by a huge amount of molecules. The fact is that in many cases it's possible to separate the degrees of freedom, for instance the coordinates of all these particles, into classes. The slow ones, for instance the center of mass of the planet, plus say vibrations or oscillation or chaotic motion, but which are much faster. And so if we average enough this system, we only see the slow motion to remain. So the essence is that of study, first of all, the behavior of this average system. So we shall consider system composed by a few slow degrees of freedom that in general are the coordinates of the center of mass, or in general are the average of something. We neglect completely fluctuations that we, at the end we shall see that are very important. And so we shall start by studying the trajectory of systems, so essentially integrate some differential equation. And this will allow not only to study the average behavior of systems, but also to develop a language that shall allow us to recognize some behavior when we shall meet them again. And so we shall talk about attractors, bifurcation, and chaos. So clearly the real systems are composed by many systems, and another approach is that of considering them as composed by extended system, still neglecting fluctuations. And so this approach is, for instance, what has been used to model conduction of heat, electrostatic, the computation of electrostatic potential, which in some sense is due to the average over a lot of paths that virtual photons can follow. Maxwell equation, Navier-Stokes equation, Schrödinger equation, Einstein equation. A lot of these equations are actually can be considered as the superposition of several elementary degrees of freedom. And when we consider only the average without taking into consideration fluctuations, we end with some differential or partial differential equation. But using very simple system, for instance, systems that can show chaotic behavior, we can use them also as a laboratory for understanding why at a certain point we have to take into consideration statistical methods. for instance, we can take one of these systems, for instance, the Navier-Stokes equation, Schrödinger equation, or simpler equation, and derive a time series, considering them as if they were experimental systems, and supposing that the time series that we obtain by simulation are actually experimental data. If one is confronted with this data, may ask to himself, are they generated by a deterministic system, a system that I can model using a differential equation, or by some stochastic system, so in a sense, a system so complex that I have at least considered some part of them well represented by something that cannot be followed with up to the more fine details, but has to be simulated or approximated by a stochastic system. And so we shall use a time series analysis in order to introduce the random walks. Random walks, which are one of the simplest example of a stochastic process. A random walk is a trajectory in which there are at least some part of contribution due to a stochastic input, something that cannot be forecasted, and we shall introduce for this not the same tools that we use to study, for instance, trajectory of planets, but other tools, for instance, probability distribution or correlation, which is essentially the Langevin approach. And probability distribution are one of the main factors that we shall use essentially for computing equilibrium properties of things, and also to investigate the problem of fluctuations and how system can be represented near a phase transition when characteristics of the system vary widely with small changes, for instance, in temperature. And this will be strictly related to the idea of bifurcation that we shall meet speaking of dynamical systems. And clearly, in equilibrium, we can use a completely different and more powerful tools. For instance, those that are originating from thermodynamics, and we shall see that we can recover or say frame the whole system of thermodynamics using the concept of statistical mechanics. So we shall spend some time studying first by recovering the main concept of thermodynamics, heat engines, entropy, and so on, and by deriving them in the framework of statistical mechanics, so assuming that the system is at equilibrium. And clearly, from a microscopic point of view, at this point, we meet some kind of inconsistency, because we have started integrating the equation of motion. They, for a system that is isolated, so the same ingredients that lead to equilibrium, they are reversible in time. I mean, if you let the system evolve for a certain amount of time, then you reverse the velocity and come back in time, you should go back to the initial state. This will imply, for instance, that a gas first contained, say, into a balloon, and then let it expand and occupy all the system. In principle, it is, so physics says, classical physics, but also quantum one, says that it is not impossible to see it come back to the initial state. But actually, in the real world, this never happens. If something is broken, it is broken. It is not come together without effort and without glue. And so this was one of the problems that Boltzmann had to meet when he started developing the concept of statistical mechanics, and we shall investigate them using also computers. And so understand why this thing. So the error of time has one sense in the microscopic world, but can go both sense in the microscopic one. Then we shall deal completely with the field of statistical mechanics. I mean, the idea of macrostates and microstates, statistical ensembles, observables, partition function, and so on. And clearly, we had to understand how to compute these things in classical or in quantum systems. And again, we shall see that this can be done by hand only for linear system or almost linear system, and for a more complex system, we have to use computers. But one of the advantages of using this statistical mechanics approach is that we can replace the real dynamics, those given by the Newton equation law, with another equivalent one, chosen in some sense at will, that clearly, if we are able enough, can go much faster to equilibrium than the original one. And so, in this way, we are able to study system composed by many degrees of freedom in a way much faster than just following the equation of motion. And this is one of the main contributions of statistical mechanics to the investigation of reality, and is called essentially Monte Carlo techniques. And so we shall play with Monte Carlo techniques and develop the main idea. Clearly, there are volumes and volumes devoted to this technique. And so essentially this is the path that will bring us from Newton law, trajectory, time averages, and ergodicity. I mean, so these are the systems described by classical quantum systems, to distributions. And with distributions, clearly we leave the idea of following a trajectory, but rather we are interested in the average behavior of a system. But the average, we have to introduce the statistical ensemble, so average over which are the constraints that we consider. This step from distributions to ensemble averages is essentially contribution by Gibbs, and the idea is that instead of averaging over time over the trajectory of a simple system, we can average over all possible configuration given the constraint, so given the statistical ensemble. And this will lead us to the partition function that will allow to separate, for instance, velocities which are essentially simple to calculate the distribution of velocity with respect to, for instance, the distribution of position, which are more complex. And so we shall be able to develop simpler dynamic, considering, for instance, only the spatial distribution using Markov processes, so that we can get a statistical trajectory that converges to equilibrium much faster than the original one. And so, again, exploiting ergodicity, have these artificial time averages using Monte Carlo and get, say, the computation of properties of the system in a much faster way. Statistical mechanics and related methods can also be used to deal with a completely different problem. One of the most interesting one is complexity. Complexity in computer science is defined in several ways, but essentially is one can take, for instance, the time required to solve a problem, and generally it is understood as in the worst case. So, for instance, to find something in by looking in a tree or in some complex data system, or verifying if a certain assumption is satisfiable or not, and so on. And this science has essentially classified the problems into solvable and hard ones. solvable are those whose complexity grows, say, as n, or as some power of n, with n the number of items, while complex ones are those that essentially whose complexity essentially grows as an exponential of n. And so everything seemed fixed when physicists entered the field and started to consider not the worst case, but the typical case. So to work with the measure, with the probability distribution, which are the tools already used in statistical mechanics. And in this case, one can show that not all complex systems are complex in the same way, because it depends on the parameters. The typical case can be quite easy to solve, even though the worst case still grows as an exponential of n, or almost all cases can become difficult. So one can have a kind of phase transition in complexity, and this is an interesting tool to be studied. And another one is still about criticality. In statistical physics, we have phase transitions. Phase transitions of second order mark critical system. Critical system, one has fluctuation at all scales, but in usual systems, for instance, magnetic ones, these happen for a very precise value of, for instance, the temperature of some control parameter, while in the reality, say earthquakes distribution, or the distribution of waves in the sea, or avalanches and so on, one observes a power law distribution like that one observes in critical systems, but without any parameter that is fine-tuned. And so one can speak of self-organized criticality, and it is interesting to study some simple problem that shows this aspect. And another tool that comes directly from statistical physics is the simulated annealing. This is the problem of finding the optimum, the minimum, or the maximum of some function. A function that clearly can, this problem can be dealt with using standard techniques, say simplex approximation, so simplex method for finding the minimum of a function that depends on a certain number of variables. But when these variables become too many, this analytic approaches do not work anymore. And so in the 70s, 70s or 80s, they started to consider the equivalence between the problem of finding the optimum of a function and the problem of finding the minimum of a statistical system. And if one considers the cost of the function to be optimized as a kind of energy, and so the minimum corresponds to the ground state of a physical system. And if one considers the effect of temperature, which is that of allowing the system to pass through a local maximum, and so going down and find the valley where the global minimum is, one can develop a method of slowly lowering the temperature in order to concentrate the probability distribution around the minimum, and so then find the global minimum. And clearly, this is a simple method to be used with the Monte Carlo simulation, not the fastest one, but in general it is quite effective. And this method has been also used to study complex, really complex systems, which are glassy systems, and glassy because they behave in some way as a glass, so they have a very slow relaxation time due to the fact that there are many minima of the potential very close to each other, very similar in energy. So finding the right valley and the global minimum is a very hard problem. And actually, this system below a certain temperature never reach the equilibrium state. They are also quite difficult to be simulated. And so here again, there is an extension of the idea of simulated annealing called simulated tempering that can be used to deal with these very complex systems. And finally, one of the topics that emerged recently in the field of statistical physics is networks, because physicists were accustomed to deal with regular lattices, crystals, and also completely disordered networks, which are bread and butter of the mean field approximation. But when people started to study real networks, say the network of distribution of energy or the network of contacts among people, all things that are quite interesting, for instance, in modeling the spreading of disease, they discovered that these networks are very different from the ones that have been already studied in physics, because they show some characteristic typical again of a critical system. I mean, very power law distribution, very broad power law distribution, and also the dynamics on these networks are quite different. And so, again, it is interesting to have at least a look to this network. So, finally, in this graph, one can say follow at least some typical say path that can be used to have a unified view of statistical physics. So one can start from Newtonian law, essentially the integration of equation of motion, to high dimensional partial differential equation, Navier-Stokes, and so on. And clearly, one of the few things that can be solved by hand in this field is a linear system. For instance, a crystal oscillation of crystals, and the analysis of essential linear system, which are linearized by a Fourier transform, but essentially are linear. And the thing that one can derive is that there is no equipartition for a strictly linear system. The energy, if it is concentrated in one degree of freedom, it always stays there. Otherwise, one can disregard fluctuation and also spatiality, so consider the system homogeneous and go to low dimensional, so dynamical system, coupled differential equation, and can study trajectory, what we shall do in the next lessons. Study attractors, low dimensional chaos. One way of studying them is through stroboscopic view, so sections, so in order to convert differential equation in difference equation, that are also called maps. And from them one can get time series analysis, as I anticipated. And so this is a way of introducing a probabilistic approach, a distribution, and then study stochasticity, trajectories, random walks, Langevin equation. But clearly, one can arrive here also considering, as we anticipated, the high-dimensional chaotic system, for instance, those that are obtained by molecular dynamics, and focus on one element. Again, one can get to stochastic trajectories, and from here one can study diffusion and for instance the Fokker-Planck equation, or generalize it to a Markov approach, evolution of probability distribution. And clearly from all these one can arrive to the problem of mean field, the tool of mean field, which is a way of dealing with the averages of Markov processes. And clearly this is related to chemistry, to thermodynamics and to phenomenological systems like cellular automata, agent-based modeling, network theory. So a lot of different methods. Clearly, starting from thermodynamics, one can arrive to equilibrium, and so to Monte Carlo, simulated annealing, stochastic optimization, and so on. And so one have in some way a local view, and one studies something that has a local view of a piece of this world, and it is interesting to at least once have an idea of all elements that compose statistical mechanics. That's all for the first lesson.